Hello. Hello. Good afternoon, Katie. All right. Good afternoon. And good day. Okay, I'm going out of order. Wait. Good afternoon. Okay. Hello, Maria. Hello, Cheska. Hello, Maria. Hello, Paulina. Uh, uh, wait. Good afternoon, Katie. Good afternoon, Stephanie. Good afternoon, Freddie. Hello, Michelle. Hello, Shy. Hello. All right. Good day. That's a new one. Good day, Michelle Q. Good afternoon, Jada. Good afternoon, Marilyn. Oh, and there is Yavi. Hello. Um, good afternoon, Michelle F. Afternoon, Maria. We said good afternoon, Paulina. We said good afternoon, Yavi. We said all right. Awesome. And Jada and Katie. Okay. Oh, and more people here. Hold on. And I don't have a board at the moment. We will fix the board. Hopefully, the board will be fixed in a second. Okay. Um. Okay. Okay, wait, let me just, while people are coming in, let me just fix the board or try to fix the board. Hold on 1 second. More people. Good afternoon, Brooke. Good afternoon, Emily. Okay, hold on. Let me, bear with me on the board. Sorry. I'll tell you, oh, thank you. Huh. Wait. Yeah, no, I don't mind. Okay, there's something in the direct chat. Yes, I don't know if I mentioned, yes, my family is a lot better now. Thank you. Yes, we are. It's been a bit of drama here. I don't know if I made that clear or if you all, what, has there been weird weather there? I don't even know. Are you guys all, hi, Chef. Hello. I don't even know what, and we will get started in a second, but yes, there's been a bit of drama here. Um, oh yeah, and I didn't tell you, and sorry, so I meant to make an announcement. I didn't have office hours yesterday. I apologize. And I meant to make an announcement about that, and I didn't. I wasn't on campus. We got a little trapped here with a lot of drama, ice storm, no power, no water for days, blah, 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 blah. But on that, so thank you, but we're fine now. Thank you. We'll draw, I mean, sick child, toilets that don't flush. I don't know. Do I want to be more specific? But uh uh hotel rooms, drama. Um, but um, I forgot. But that did mean that I wasn't in office hours yesterday, which I apologize. Which means a couple things. Number one, but of course we still have this exam Thursday. So number one, we're gonna do more. I didn't promise, but I am saying today will be more prep for the exam. Partly, so today will be more like this class. Think of it in a way, at first at least, as office hours. Like I'm going to continue this Q&A trend from Monday. Hopefully that's helpful. I have something ready if you don't have any more questions, but the thing that I have ready is meant only to help with the exam. Like one thing I do know from experience, even if I think we had great questions and everything, yes, but hold on, I'll get to that. The point is, the last thing I want to do the day before an exam is just like get back to new material that isn't on the exam. Like that's just confusing and stressful. And it doesn't do anybody any good, in my opinion, like to do a bunch of new material like the day before an exam when everybody's focused on the other stuff. So today, in part, anything that you might have brought to office hours as a question or something, please do bring today. I mean, please raise today, even if it's in the direct chat, just Monday. It's the least I could do. Please also know that if you have like a real crisis or a jam, I could possibly do Zooming or things like that tomorrow if people want to talk to. I mean, I don't want to make a big production of that, but reach out to me directly, and I'll see if I can make an arrangement at some point tomorrow. That's number two. But number three, more to the point. So all we'll do today is continue to try to be as prepared as possible for this exam. But you should also know, I think it's clear, but just to be clear, not only was that extra video from last summer that you guys found, I posted that, but also the Q&A session from the other section. The other section's normally not on Zoom, but it was yesterday because I wasn't there. So the other section was on Zoom, and they had totally different question. from yours? Oh yeah, their question yesterday was specifically, so it wasn't totally different, but their question was part D. Oh yeah, my lord, yes. They in the other class, they asked about part D of question, not part D, part 6 of question 3, which definitely is like the punchline of part of problem 3 and exactly the point that I didn't get to in your class yesterday and Monday. And even though probably it is covered in that summer video that you found, which I haven't seen in a while, just to say, I do a full, like overly detailed walkthrough of part D of question 3. You know what I'm saying? The last part of question 3. I walked through in the other class and I posted that video. So please do, I mean, in your classroom. So, you know, and there too, I get, okay, I'll just bring this full circle. Pardon me. Like at the beginning of yesterday's class, of Monday's class, you know, one of you in the direct chat asked, like, how far are you supposed to go with givens and assumptions in like part 1, problem 1, for example, right? And I went on this whole long thing about how to show the differential equations and the cosines and all that. And then I said, oh, but as far as like energy and the path integral for work and the closed path integral for potential energy and like all that energy stuff, you don't have to talk about all of that in question 1, problem 1, because like it's not relevant to question 1, problem 1. But all of that comes up in the last part of problem 3. That's where like that's like the one opportunity in the exam to ask you about all that energy stuff, and to be clear, that energy stuff, specifically integral and closed path integral, that really becomes important at the end of in the last part of the course. So short story long, if you want a full expansion of like what's expected of you to say about those kinds of things, watch the video from the other class from yesterday. I go into all that there. Okay. So hopefully this is putting together a lot of different, you know, I mean, if you could sit down and like actually scroll through all this stuff, you know, hopefully you really have an opportunity to do very well. So that said, I'm going to look in the chat in a second. So today, as soon as I get my board working, which it will, we will just, even if it's like a little overkill, like I don't usually, to be honest, I don't usually spend this much time just trying to like get everybody ready for exam, but I don't mind doing it if it makes it all more comfortable. Just also let's make really good exams. That would be a benefit of all of this. Okay. Oh, there is nothing in the chat. Oh, was this upset? No, oh, you don't know. I know how to make electricity. Yeah. Yeah, well, right. Sort of. I don't know how to like replace a down transformer that got hit by a tree on somebody else's property, but is this upstate? No, actually, I don't. Oh, do you not know where I don't know if this is I don't live upstate. Can we say this on recording? So I live in Maine, actually. That's drama, right? But I didn't always. I mean, it's a bit of a post-COVID casualty kind of thing. But you know, for what it's worth, up here in Maine, okay, I'm going to get back to this, but up here in Maine, which is very different, because I still, in my heart, of course, my heart is still a little bit more urban than this lifestyle. When the people ask for my address, I say that I live on West 242nd Thousandth Street, and they don't think that's funny, but I do. Okay, hold on, I'm gonna get the board ready. Okay. But I'm gonna get the board ready, and then I'm gonna be looking for questions from the chat. No matter what, we're preparing for the exam tomorrow. So even if you don't have questions, believe me, I've got something to do. But oh, you didn't know that? Oh, yeah, it's crazy. Yes, it's sorry, this is not the time to talk about this, but yeah, I come to New York. So, but occasionally, that's why I occasionally don't, because things happen up here that make it very difficult to get there, or make it difficult for my family to function here in the woods or whatever. So, but yes, I come every week. It's a little crazy. It's really because whatever. Okay, yes, hold on. I'm just fixing the board. But the fact that you did not know that means that I do an okay job of managing to some extent, so that's good. Oh, to some extent. Hold on, just fixing the board, bear with me. But you're preparing your questions about physics, not about my life, as we speak. Okay. As we speak, you are scrambling to get questions. Oh, I know that. Oh, I know that. Is that me? No, that's not me. Okay, the board should work now. I can't fix a power grid transformer, but I can fix a board, I think. Did it? Okay, and we are recording. Okay. 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 Okay, so the board's working, so we're recording, so we're okay, closed caption. All right. So again, this is for anybody who's just tuning in, this is gonna be Q&A for the exam, more Q&A for the exam. The car problem is all the problems are me. Of course, the problem. I mean, the car, you mean, of course, who writes these problems? I mean, he was in the, yeah, yes, of course, that was me. You, I do no, Cheska. I'm not even gonna make a joke. Like honestly, I've. It was hard enough to leave New York. But it's so hard to leave my job that I haven't done it. I can't do it. But no, right. I couldn't pay. I wouldn't pay you enough. You can't pay me enough either. It's not about. Obviously, they don't pay me. No. It's not about the Toyota. You didn't like the Toyota Camry? Okay, I think it was actually a Corolla, to tell you the truth. My first car was 1975 Toyota Corolla. No, it's not about fear. You understand that every week. Also, just to be clear about Felix, because we used to live in Brooklyn forever. He's a Brooklyn boy. I mean, we're all and he still won't eat any pizza that's not from Pizza Crew on Nostrand Avenue, and he won't eat any bagels that aren't from Lula Bagels on Nostrand Avenue. And he's right. I mean, Maine, you don't move to Maine for the pizza and bagels, that's for sure. So almost every week, somehow I make a point of getting those and bringing them home to him. Even when I used to take airplanes, I would bring them on. Yeah, no, the car ride, it's all long. Yeah, okay. The train, it's all based on real. Okay, I'm gonna read this quick because I know we got to get back to the exam. I'm amazed you didn't know this. Actually, I'm thrilled. It means I guess I'm doing a good job of doing whatever. Of course, your homeworks are based on real life events, except that some of those real life events are from. I mean, I've been doing this for 30 years, not this commute, but I mean, some of those problems were written a long time ago. But yeah, of course, they're all real. To be okay. Wait. Okay, interesting. Okay, now I'm seeing it is all very funny what you're saying, but I know some people will get rightfully frustrated if I just talk about my life the whole. But so now I'm seeing physics questions, and I want to in the chat. I'm going to respond. Wait, and one thing. Wait, oh, listen. Sometimes I fly. Yeah, it depends on that. But Queens, we're not getting into a Brooklyn Queens thing. Okay, hold on. Okay, so I'm going to respond to questions in the chat now. Some of them are private, some of them are public. One thing is, just to be clear again, as you know, I just want to be clear about this. Like, the practice exam is for you guys to practice. It is definitely the best way to practice. It is, and we keep going over the solutions and stuff like that, like with the videos and everything. So the good news is, right, you get this practice exam where you get to see what's expected before you do the exam and all of that. And you get to work with each other through the exam and everything and watch all the videos. But the bad news, just to be clear, is the practice exam is not for a grade. As you know, you don't get graded on that. You only get graded on the real thing. And similarly, there isn't actually time, unfortunately, for me to do feedback on the practice exam. The practice exam is for you. And for you can get feedback from one another, and you can check your answers with all the videos and everything I post. But I can't actually, especially now the day before the exam, I can't, and I could talk to people, but just to be clear to everybody, and other people have asked, for good or for bad, unfortunately, no, I can't take the practice exam from anybody. It would be a false. I think I just answered that question to someone who wasn't here, but all right, well, I'm gonna move on. But so anyway, just to be clear, unfortunately, I cannot do an interchange with the practice exam. That's for you guys. That's not for me. I can talk to anybody about anything, but if it would be a false promise if I suggested that I could mark it and get it back to anybody before this exam starts. Okay, no problem. But just to be clear, unfortunately, I cannot. The practice exam is for you guys. That's for you, not for me to look at, unfortunately. All right. Now there's another question in the direct chat. So someone's asking in the direct chat, this is funny. And they say, could you maybe go over question 4? Okay. I'll tell you what. Okay. Sorry about that. Hold on, just also one sec. I have things to say about question 4. Okay, I'm not surprised that that's the question. That is not an unfair question. I mean, none of the questions are unfair. Oh, wait. Yeah, right. Okay, I'm seeing other things in the chat about question 4. Okay, so 2 people have asked about question 4. Question 4 is the most open-ended for sure. It's it's like the essay or whatever. It's like the free response question where you have the most reign to just do it your thing. And then yes, there's like a grading rubric where I give you points if you cover certain things, but you have to cover, you have to cover issues your way. So it is hardest to predict how well you're going to do on that one. That's for sure. And it's the most conceptual. Now, there's a couple of, so I had a feeling today might be a lot about question 4. Number one, it is definitely the place in this whole exam where I'm really wanting you to, watch any and all videos you can. I mean, I'm sure there's more videos where I walk through it more specifically that we haven't even identified yet. And whatever one of you finds, like, because I've talked about that a lot. I mean, I'm sure there's one, even not necessarily labeled a midterm review, but the key phrase okay, first of all, the key search terms, so to speak, for question 4 is staggered phase collection oscillators. Like if you're doing a YouTube search, I mean, particularly like of my, and yeah, I don't know if other people do it this way. I mean, obviously but if you're doing a search, like in the channel, like you're looking for, what collection phase staggered oscillators. Those are the key terms. Okay. That's number 1. And there, yes, I want you to see old videos or look at your notes from the day that we did that. And I want you to, if you are ever to get together with a friend and prepare for this exam or while this exam, if there's anything you should like debate about or discuss about with your friends or your colleagues, it would be question 4. Because question 4 is one of those things where I'm like trying to get you to see a large concept and you don't see it until you see it. And then when you see it, then you see it. And then but then there's a lot of bases to cover. So first of all, on that one, yes, understand it's harder to practice that one in a direct fashion. It's more about debating it until you understand it. But that nonetheless, yes, there's this like grading rubric. And so someone's asking, it has 4 different parts. Wait, am I reading the wrong? Oh yeah. It has 4 different parts. How strict will I be on grading those parts if it was answered not in labeled parts? Like if someone has put all their ideas and explanations on the page and understood the correct conclusions and assumptions, but say they forgot to explain a variable or something. Right. I mean, that's a very fair question. So I'll say a couple of things. Because this is open-ended, it is true that you want to spend even extra time. It doesn't matter what order you do things. Well, no, I shouldn't say that. That's not true. In question 4, definitely every time you think you're doing something significant, like answering something that you think you should be getting points for, you definitely should spend the extra time to label what you're doing while you're going. Like the more you can tell me, this is what this means, this is, the more, maybe use 2 colors or something like that. The more you can be like arrow. So this is the math equation that describes the whole thing, or arrow. This is where I derived the meaning of the angular wave number. The more you can label, definitely the better. That's number 1. Number 2, yes, even there, it's like anywhere else. If you really show that you really get the core of the issue in a big way, I will be generous. I mean, I'm. It's still more about the big picture than the small picture. I can be generous and forgiving if you like missed a little thing here or a little thing there, but you have to give me reason to be generous and forgiving. You have to like, compensate. You have to show me that you really have gone deep on some important aspect of it, such that by the time I'm reading the little things, I don't care as much. And I'll be more specific in a second, but yes, there will be generosity there. And also, it's also harder to grade and just in the same way that it's harder to write. But the main thing well, hold on. I'm even going to look in the chat if there's more. Yes. So someone has put in the chat here. One thing is someone has put in the direct chat about question 4. She or he said, it was a combination of all that we learned working together to explain the concept. It's explaining all the concepts and equations and how they are interchangeable. Like that, or it's certainly interconnected. Yes, there's something about question 4 that's forcing us to put together everything into one unified package. And that unified package is a wave. Like on a big picture, and I believe me, I will get more specific in a moment. Like I do think this is, a good, it's where I kind of figured people were going to be asking today. And I will do kind of a walkthrough in a second, but there's like so many walkthroughs that I'd rather give you another, spend your time a different way. Question here, but I will start writing things to make this clear. Hold on a second. This is just, this whole PDF right now, by the way, is one big PDF that contains the answers to your questions from Monday, plus whatever I was answering to the other class yesterday. It's like all in the same PDF. And I'm going to continue in that same PDF right now. So when I post this, just to make this more streamlined, so this is like one big study document, if you like, or, it's just like all the Q&As just all together here. So, all right. So here, so there'll be redundancy when it's uploaded is what I'm saying, but okay. First of all, the big, oh wait, I'm looking, wait. Yes, no, I believe you did right. So the person in chat said that they explained, yes, as long as you explain how you're trying to show how all the different details of simple harmonic oscillation come together in order to make wave motion. Like that's like the big goal of this. Like, I mean, because that's what's cool. I mean, that in nature, we have these things called waves. Waves are cool because they are unthingy things, but they exist and they can be real. In other words, a wave is immaterial motion, but the reason it's real and it's not a ghost or an illusion or trick is that it's immaterial motion that is brought about by a bunch of materials moving in a very specific way, right? That's the big picture that you're trying to show here. Now, let me be more specific. You're trying to show that if a bunch of material particles all undergo simple harmonic oscillation in a very specific way, then they will give rise to wave motion. What is that very specific way that I keep saying? Well, in effect, what I'm saying is what you're really trying to, well, I'll write it down. But what I'm saying is as long as you have a bunch of objects that oscillate harmonically in time, in other words, oscillate cosinusoid, if you have a bunch of objects, each of which oscillates cosinusoidally in time, but these cosinusoidal time oscillators are arranged so that their oscillations are cosinusoidally spread out in space, then you have wave motion. I'll write that down in a second. But in other words, what I'm really trying to say is that problem 4 on this exam is asking for you to fully walk me through the English, the picture, and the math of lab 3 backwards. We're really trying to do lab 3 backwards here, by which I mean, in this question 4, you're trying to show that if you arrange a bunch of time cosines into a space cosine, what you have is a wave. That's the bottom line. I mean, obviously there's details, and I will get to the details in a second, but you're really trying to show now, even that English is kind of awkward, right? I mean, and that's why the heavens invented math. Like, I can't even say it perfectly in English. The only perfect way to say it really is in math with pictures. But here's some basic steps that you have to cover in your version of part. I mean, I know I already gave the grading rubric, right? But I'll even admit here too. Yes, it's tricky. It's like an essay. Like, I want you to do it your way. I want you to show that you've processed this through your understanding. But even here, you're trying to derive something. You're trying to show that if we start with the assumption of a bunch of oscillators, and that is an assumption, you can assume you have a bunch of oscillators, and you can assume that anything we know about oscillation is already true. Like, you've already proven it in everywhere else in the exam. So what's a given is that you have a bunch of oscillators. I'm just going to fix the view on the screen, sorry. What you're trying to derive from those givens is that if you arrange these oscillators in a certain very specific way, like if you set them up in a certain way, if you arrange them in space in a certain way, and then you time all of their oscillations in a certain way relative to one another, then it will follow that we'll get this wave described by this certain wave position function, right? I mean, you are ultimately trying to, so in English, you're trying to derive a wave. You're trying to show me that it makes sense, that you'll get wave motion from these oscillators. But in math, you're trying to show me in the end, therefore, we will get the position function, the equation that describes a wave. So it is here's my point. It is a derivation or a proof of sorts, an argument. Therefore, order does matter. I will warn you that in this question, like you can think about it however you want, you can do different drafts, but once you present it here, order does matter. So before I lose, so in a second, I'm going to tell you some things like not to do or that people have done in the past that shows confusion. Um, Let me finish the notes that I was just writing so I don't lose the thread. I'll go back a page in a second if you want. Let me just write this before I forget. Okay, wait. I want to go to the next. Um, 1 second. Okay. 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 So I'm gonna go to the next page unless you tell me to go back. Does anybody tell me to go back? No. All right. So I'm going to the next page, and then I'm gonna stop and say something about this. But I'm gonna flip page one more time. I'm gonna go back to this page because this is the important, but give me 1 second just before I forget. Okay. Um, uh, okay. I have something even more specific, believe it or not, to say about all this, but the roadmap. Here's the roadmap in the notes right here. Maybe I've said it more. The roadmap is like you present the oscillators. Explain what you mean by identical oscillators. Like they're identical. That means they all have the same, for example, K and M, which then means they all have the same omega. Like explain that. And then explain how you're going to just, but then everything we know about that is understood. Or you could say like C problem 1 or whatever. Then you're going to explain that you're going to distribute these oscillators in a certain way. Like you're going to make them so they each oscillate vertically. You're going to make them so that they each oscillate along a y-axis, but you're going to arrange them along an x-axis. Or yeah, that. I mean, actually, what you are. I mean, it doesn't really matter if it's like this or like this, but however each one oscillates, we're calling y, and however they're arranged, we're calling x. And you're going to say that literally not only are they going to be on an x-axis, but they're going to be equidistant from each other, from one another on the x-axis, right? And be specific and like label the x-axis numbers like 0, 1, 2, 3, 4, whatever. And then you're going to say specifically that all of these oscillators have the identical angular frequency and they're all identically far apart from one another. The oscillation axis is one axis, the distribution or the arrangement axis is the other axis. And then here, yeah, and then you're going to, like I do in the lectures or whatever, write down an equation for each one of the oscillators. I'm giving all these answers because this is hard enough to do when you know what you're doing. So it's not about mystery. It's about, I really want you to understand this. So the equations I'm talking about, it's like for each one of the oscillators, you would write something like, something like this. You would write something like, for each individual oscillator, you would write something like for the third oscillator, you would write y sub 3 equals a cosine omega t plus 3 times some number that's in there that might be like pi over 2 or might be pi over 4 or something. And here's where, again, pro tip right here, I didn't even write it down, but like, you write an equation under each one, and the third one would be 3 times some number, and the fourth one would be 4 times that number. Now, what is that number? In most of my examples, I tend to use the number pi over 2. But one pro tip, I should stop saying that, is that I keep on saying whenever I use pi over 2, it's an example. And one way you'll know if you really understand this problem or not, one way you'll really know that you understand what's going on is if you really understand what I mean when I say that pi over 2 is just an example, i.e., could you set this up and explain it for a different number, like say pi over 4? In fact, that's my highest recommendation to anybody that's like still listening at this moment. When you're either practicing or doing the real thing, you'll really know that you get this if you can make an example where the thing is pi over 4 rather than pi over 2. What does that mean? It means then can you make a drawing? Because you're going to draw all these springs, right? You're drawing them equidistantly with, well, the drawing would look different if you wrote pi over 4 or pi over 2. And you'll understand that difference in the drawings, and it would look different if you did pi over 8 or pi over 16. Now, the smaller the fraction is, the more springs you'd have to draw, and the more precisely you'd have to draw. So at a certain point, it becomes like a pain in the butt. But if you even get that, if you even get yourself to the point where you're like, oh, I don't want to draw pi over 4. I see why he just keeps drawing pi over 2, because it's like harder and more annoying to draw pi over 4. If you even see that, then you see something. Like if you see what the pi over 2 really means in the drawing, you see something. Now, the real way you could really satisfy yourself and impress me or whatever is if you make a drawing where it's pi over 4 and it's right, then I really know, okay, they're not just copying me. They get it, right? Or pi over, so there's but in any case, each one of these springs has an equation like y sub 3 equals a cosine omega t plus 3 pi over 2. So you like write out all those equations. Then you show, aha, there's a pattern to these equations. So we could put them all together and write them as one equation where we swap out the number 3 and we put in the number x, or the variable x, right? And you do that. You show how these whole thing, all of these equations can be collected into one. First of all, before I go any further, one common error that people have made in the past, one common error, if they don't really get what's going on, but they're like trying to do a bunch of stuff and like trying to copy things from various videos or notes, a lot of times people start with that equation. They start with like with an equation that they start with an equation that looks, where'd it go? This. A lot of times people will start with that equation and then start explaining it. And maybe even, and sometimes I've had situations where people will explain it for like 4 pages, and then they get to the 4th page, and then I see all these pictures and everything that I'm talking about right now, and they eventually have like a bunch of details that are kind of right. But if they've started with that equation, unless they've made a real point of explicitly saying, I'm going to do something creative and clever here, bear with me. Like if they start with that equation, then they've missed the whole point. They're not deriving it. They're just going in a circle. I'm asking you to show how that equation, how waves come out of a collection of oscillators. So I'm saying the roadmap is you draw a bunch of oscillators, you draw their individual equations, you then say how their equations could be put together, and you'll know. Here's my best answer in a way to this whole question of like, how do you do question 4? Or how do I grade it and how generous am I or whatever? One of the key things I've always looked when I look at these question 4s, first of all, I look to see is that picture up at top, like, are they starting with a bunch of oscillators? Are they starting with individual equations, not a collection? Do they get that much? Are they explaining the nature of each of these oscillators? And then once the person starts putting their equations together and getting to a final equation, then the next place my eye always goes is I always look to see, did they make a big point of explaining K? This K, the K, can you see on the screen? Yeah, this K that's boxed at the bottom, the angular wave number. Big pro tip here is that is the one new constant that comes out of this whole discussion. Like that's the thing we didn't know anything about before, right? Each individual oscillator is already described with an omega and a T and an A and a whatever, right? So all of those things are oscillating concepts that you've covered through the rest of the exam. But when you when you take these oscillators and you distribute them in space, and you make it so that each one is out of phase each one is out of phase from its neighbor by an amount that, no, let me start again. Each one is out of phase from the 0th one by an amount that corresponds to how far away it is from the 0th one, right? Like this is the key to the whole thing, that we've arranged them so that the pattern of their phases corresponds to the pattern of their arrangement in space. Like that's what makes the wave work, is that the time oscillators are spread out in space in a pattern that corresponds to their phase shifts. So they're all in phase with one another in time and in space. So it makes a wave, right? That's the key conceptually. So the key thing that comes out mathematically from this arrangement of staggered oscillators is this new constant called K, the angular wave number K, which measures sorry, I'm looking for a way to say this. Well, K, which measures radians per meter, right? K, which is in literally the wavelength, which is literally 2 pi over the wavelength, just like angular frequency was 2 pi over the period. So K is how many cycles this wave is making per space. That's the new thing that comes out of this whole thing. That was the newest piece in lab 3. If you want to know whether you're really giving me what I'm looking for in this exam, you'll go through this roadmap and do all this in detail. And then when you get to the point of introducing K, you'll make a big point. Here's where labels and everything come in. Make a big point of the fact that you are now here at this moment introducing K. Like that's the rabbit that is being pulled out of a hat, seemingly. But you're showing me where it was hiding in the hat. Like that's your job, is to, I can't emphasize this enough. In fact, I mean, if you stop watching the video now, like the big answer to all the questions about question 4, like if you vaguely know what's going on with question 4, but you're not like really sure if you're doing the right thing, or you kind of get it, but like, what am I looking for? In the end of the day, what I'm looking for is, can you walk me from a bunch of springs to one ripple? Conceptually, can you walk me from a bunch of springs to one big ripple or one big pulse? Mathematically, can you walk me from a bunch of springs and show how once upon a time we thought of things as y equals a cosine omega t, and now we think of things as y equals a cosine omega t plus k x? If you can actually point to the moment that k comes into your work, when you're like, here's therefore why we introduce this thing that we're going to call k, and here's what k means, and then you land at the final equation, then you can take that final equation, this thing, and differentiate it twice, really 4 times, 2 time ways and 2 space ways, and show this thing that is the wave equation, and then show, and then say, you know, what that means if we stand back is that every little piece of this wave accelerates down or up, accelerates toward equilibrium at a rate that is directly proportional to how bent the string is at that point. And show, like, so see, once K came into the discussion, whatever we used to believe about masses being stretched away from their equilibrium place and accelerating back to their equilibrium place in a proportional way, like now we're saying about strings being bent away from their equilibrium line and racing back to their equilibrium line in that way. What I'm saying, I keep saying I'm saying it, but I'm not saying it. I'm saying, consider your main goal of this whole thing to actually alert me at the moment when K arises and explain to me how it arose and what it means and how it gives us this final equation. It's really about K, I guess. I mean, and when I'm grading it, honestly, like, especially when I'm in a rush, if someone doesn't talk about K at all, I'm like, they don't know what's going on. And if someone and here's a common thing that people do, but it's not what people will do. They get the point that I'm saying, explain each term in the equation. So they'll do stuff, and then they get to the equation, and then there's the equation, and then they like circle each part, and they do like A means amplitude, omega means angular frequency, K means angular wave number. Thank you, Yaverbam. Have a nice day. Right. And then even if they say more words, and I'm not trying to mock anybody, but even if they say more words than that, the truth is, if you give the same level of explanation for each one of those variables as you give to K, something's wrong, because all those other variables we've been explaining through the whole rest of the whole exam. We understand the other, you couldn't be putting oscillators together if we didn't understand the other variables. The question is, can you, how did they all give rise to K? So really the litmus test is both, can you explain K in detail? And yeah, I'm sort of giving away my subconscious thing when I look at these things. I mean, I never really consciously thought about it, but I'm always looking, did they say a bunch about K? And did they show, not just say what it means, but don't say it too early and don't say it too late. Like, show me the moment that K arises, like why we suddenly discovered the need for or the ability to have this thing called K. If you can flag that moment and be like, so this, and now we have K, and this is what it means. That shows me that you've done a real argument. You've done a real derivation. You have brought us from some old understanding to some new understanding. So it's about K. I mean, it's about K, if that helps at all. Now there's even, is there any more? I don't know if I just, I yell when I get, I'm just looking at, hold on. So I'm going to pause for a second. Just raise your hand if that meant, and if you're, did that help at all? Or is that clear at all? Yeah, okay. Thank you. And thank you, Chris. Thank you, Maria. Thank you. Okay, thank you, Katie. Oh, yeah, and Katie, since I think, yes, thank you. Okay, now I can say something even worse or better. Wait, what time is it? What time? Oh, okay, that took a lot. I will say this. I don't know if it's good or bad, but at 12:22 today, something got dropped. Why is it dropped if it's upload? Oh, because I guess on your side it dropped. Anyway, something at 12:22, a new thing went into Google Classroom that may or may not be helpful, because the one thing I sort of guessed that maybe today people would ask about question 4, and it does. I do know, like, I understand that what makes question 4 is it's more free form. Like, you don't know exactly what I'm looking for or how I'm going to grade and stuff. So actually that's all, I mean, then that's on purpose, but whatever, that is what it is. But so you might notice that in Google Classroom, I put a broken down version of problem 4 that I use for a non-calculus version of this class, who shall remain nameless, but whose name rhymes with Shmono Shmoo. So I put a broken down now there aren't any answers in it. Maybe I could spend the rest of, I could try to give you some answer right now, maybe, but there's a broken down version of the same problem, like, but like a more traditional, like solve for this, solve for this, solve for this. I'm happy to, I could walk through it sort of for the next 22 minutes or not. It's not meant to give you more work before an exam, but using that as your practice problem for question 4 might help a lot. Like, just, you might get your thoughts more. Oh, Jesus. All right, I'll compromise. I can't believe you're putting it on that level. All right, so hold on. So I'll show you what I'm talking about. But this is a mixed blessing. Like, it may be, but for those of you who like more ways to look at something or more whatever, more support. Hold on, I'm looking to share the screen differently. One second. Okay, so what's on the screen now, this is, okay, it's a collection of phase-staggered oscillators. It's like the same issue. It is the issue. This is a more traditional version of the question. Now, what's your version going to be on your real exam? I mean, now that I'm putting this out there, maybe it'll look something, it will look somewhere in between what your practice version looks and this. Whichever I ultimately think is going to make it easier on people and easier for me to grade is what I'm going to do. I'm not going to try to trick you at the last minute, but this might help you somewhat, like, see through. So here in this version, the whole first page is the givens, but it sort of gives you numbers to work with. So it says, like, you have a bunch of oscillators, and like each one has a mass of 20. It doesn't tell you the K. That's sort of on purpose, but you can make up a K for the moment or just write the letter K. And it says, it's sort of guiding you, like, put, the whatever, like I said before, make them all vertical, put the first vertical one at 0th position, and then the next one at 1, et cetera, et cetera. And then it says they're all set in motion at the same, but they're at a different place in its cycle at t equals 0, right? So then here, the way it does it in this example is it actually gives you the final equation here so we have to make a choice of which so this is whatever, this is to help you. This says, imagine that the whole thing could be derived by this equation. Now, again, your job is to derive this equation. That is your job. And your equation is not going to have numbers in it. It'll say y equals a cosine omega t plus or minus k times x. But here it's giving you an example. Okay. So, and then it's to guide your drawing. So you draw the drawing that I just described, but now, okay, I'll sort of give you, at least I'll talk you answers here for the moment. When you draw this thing, it's using pi over 4, an example. Like you'll notice, it's treating k as pi over 4, right? I mean, it's saying k equals pi over 4 for this example. So that means that the angular wave number is pi over 4. What does that mean in English? It means it's the phase step. Pi over 4 means that's the number of radians per every meter. So, I mean, technically in this case, every centimeter, but it means that every time you go over 1 centimeter in the drawing, or every time you go to the next spring, then the next phase is pi over 4 more than what it was before, right? So it means that the very zeroth spring doesn't have any phase constant at all. It starts at, so when you're making the drawing, I'm not going to do this for you, but I'm telling you, like if you were to make this drawing as a practice for what you're doing in my exam, if you were to make this drawing, your very first oscillator, your very zeroth oscillator would be at the amplitude position, right? At the highest possible or the lowest possible position in its motion. And by the way, that amplitude position would be 0.03, right? As this equation tells you. That's why this is, I think, hopefully good practice. So you would draw a spring whose mass is at 0.03 on the y-axis. And the whole thing would be at 0 on the x-axis. Then the next one is supposed to have a phase. That the next spring is the first spring, so to speak, spring number 1, because you just drew spring number 0. So this one is supposed to have a phase shift of 1 times pi over 4. So your next spring would be pi over 4 out of phase from the original one. What does that mean? The key is to understand that a full cycle is 2 pi radians. A full cycle means there and back, 2 pi radians. So if two springs are 2 pi out of phase with each other, it means they're not. It means they're both in the same place, right? But if a spring is pi out of phase with another, that means that while the first one is up at amplitude, the other one is down at negative amplitude. If they had a phase shift of pi, right? If they have a phase shift of pi over 2, that's a quarter of a cycle. So that would mean one is at the amplitude while the other is at equilibrium. This one's pi over 4. So it means half of that. It means while one is at amplitude, well, the 0th one is at amplitude, the very next one is halfway to equilibrium. I hope that really, in fact, I'm going to pause for a second. So just raise your hand if that makes sense so far. If you're okay. All right. Thank you. So, and then, okay, great. Okay, thank you. So, and then you go on and on like that. Then the second, so that was the 0 and the first. Then the second one would be at equilibrium. And equilibrium means your x-axis, right? And now for the third one, you fall below the x-axis and you have it halfway down, and et cetera, et cetera. So you could draw a drawing for practice based literally on the numbers being given in this equation. Again, please remember that probably your practice problem, I'm asking you to derive the equation. So don't start with the equation. But again, this hopefully just helps you practice. So you draw all those oscillators, and each one is now separated by pi over 4 in phase. And that's the meaning of angular wave number, K. K is the phase step, the amount of phase that we increase per each unit of space. Okay, so you would draw all those out. And what is the 8? So so that's what the 0.03, and you label in your axes, like label. And you're in the picture. Like, here's equilibrium, here's the amplitude, etc. So I've used all the numbers in that equation. The 8 pi in that equation, that would be omega, right? That's the angular frequency. So that means, what does that 8 pi mean in my head? It means that each one of these oscillators is going to do here's where I'm giving away answers right now, I guess. I'm sure we're about to see that these are the questions, but if I see that 8 pi right before the t, I know that means that's omega. So omega's 8 pi radians per second. So I know that this thing is doing, each one of them, every single one of them, because they're identical, is oscillating at the same rate of 8 pi radians per second. Well, there's 2 pi radians in the cycle. So that means each one of these is doing 4 full cycles per second, right? Like, I could see that. And that means in my head, if I know each one of these has a standard frequency of 4 cycles per second, that means 4 hertz, right? Each one of the springs has a standard frequency of 4 hertz. Well, that means that each one takes a fourth of a second to complete a cycle, right? If it's doing 4 cycles in a second, it's the reciprocal of that is it's taking 1/4 of a second to complete a cycle. So the period for each one of these, the capital T, is 1/4 of a second. So I already, and a lot of that, I mean, that's hard to like draw. But anyway, again, this is a little bit going backwards from the way that I probably ask you on your exam, but I think it's good practice, and I'm going to keep going. I will give the answers. I mean, 14 minutes. I'll give the answers to the rest if it helps, but I do see the things in the chat, so hang on a second. Yeah, okay, so Chris, right. So, yeah, right. So question 4, good stuff in the chat. Yeah, question 4 on the exam is really sort of asking you to show. It is technically it's lab 4, yes, but lab 4 doesn't like have a lot of math in my judgment. This is like we're really showing the underlying math derivation that underlies lab 4 in a way. But yes, what I really believe is this question 4, like, let me back up for a second. Lab 4 is lab 3 in reverse, in my judgment. And this question 4, is that it's doing the math of lab 4, but the only way that you could really understand it, or it's testing whether you really understand whatever happened in lab 3. And this larger understanding that I'm trying to get across is that, on the one hand, a bunch of harmonic oscillators that are out of phase in a very spatially specific way make a wave. Or similarly, if you break down a wave into its constituent parts, if you break up that, so what I just said was in effect lab 4. What I'm saying now is lab 3. If you break a wave into its constituent parts, what you find is cosinusoidal harmonic oscillations in time and space, right? So it's either way. It's like we're looking at how do you build a wave. So one way we're looking at it is we're building one, and the other way we're looking at it is we're taking one and breaking it apart. But either way, the new piece, like the new math, and look, why are we spending so much time on this? Let me say again, we're spending so much time on this because an oscillator, as mathematically rich as it is and as fundamental to nature as oscillators are, they still are just particles going back and forth, back and forth. Like oscillators are super important and super fundamental, and the math gets super cool. But nonetheless, an oscillator is just a particle going back and forth in space. It's still a physics 203 kind of idea. But what the weird thing is that if you take a bunch of these things that are going back and forth, and you arrange them in a certain way, then you get a kind of motion that is suddenly divorced from either piece. Like the key thing of a wave in the end, remember, wave motion is immaterial motion. It's a different kind of beast, and it's powerful, and I think it's exciting. But even if you don't think it's like intellectually exciting, you certainly know that we live in a world governed by motion, but not motion of stuff, motion of information, right? Like this whole class right now, like I'm sending something to you. Every minute I'm yelling at you. I'm sending something to you. First, I'm sending something to my screen called, sound, right? Then weirdness is occurring. And like everything I'm sending is ultimately electromagnetically getting sent from my screen to like a server somewhere, all that, like, and then to your screen or your computer, right? And like, I'm not trying to be dramatic, but I kind of, and then it's coming out of your screen and then going to your ear. I'm saying something definitely traveled. My words, if nothing else, are traveling to you. And my stuff that I'm writing on the screen and blah, blah, is traveling to you. There's a journey that is occurring. There is motion. Therefore, it's physics, right? Like something is going from me to you in space and time. So it's physics. But the thing that is going from me to you is not a thing, right? Like it's physics. Physics is study of the material world. But what I'm sending you is not material, right? So it's worth. So of course, the explanation of it would have to be a little bit hairy and a little bit involved. And this is the kernel of it. What we're doing right here in question 4, we're trying to figure out how you can put a bunch of material things together and get something immaterial. And the answer is the material things have to, each one of them has to oscillate in time while those oscillations are arranged in a very specific way in space. The key extra element that transitioned us from oscillation to waves, the key extra element was space. And that's captured by the angular wave number, which measures cycles per space, as opposed to only in the past, we were only measuring cycles per time. Like that, okay. Oh, good. I'm glad. No, okay. And you have to leave her. Okay. But no, I'm glad if Chris is picking up it. Like I really am I am throwing out something. Like again, I'm trying to keep it focused so you do well on the exam. But the reason for this question 4 thing, this question 4 is the transition from all this slog that you've been doing with harmonic oscillation math to the slog of wave math. But we're trying to transition. We're trying to show you how because otherwise it is a rabbit in a hat. Like wave motion is bizarre. It's totally bizarre. What's the only more bizarre than wave motion is that most of us just take it for granted as like, well, yeah, duh. And then the electromagnetic waves like send crap from my internet to my ear. Like what? Like just understand that wave motion is stuff moving through space that isn't stuff. What is it? It's raw information. And we're going to get more into that when this test is over and the other, stuff. But so here we're trying to pinpoint exactly like, wait, what? How did we go from something scientific and something like seemingly tangible to something so intangible? The answer is weaving cosines in time and space. Cosines in time is the whole rest of the exam. This piece is adding the dimension of space. Okay, so okay, 7 minutes. I'll give answers now. Okay, I think I will. All right, so you draw the diagram. We just talked about that. So this is a good guide to all this thing here says make certain all relevant axes, constants, and variables are explained. So this is more of a breakdown to like the grading rubric that someone was asking about before. Like make sure you got all this in your diagram. Then it says any numerical blah 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 blah. All right, then it says out of nowhere here again. This is sort of going back. It says to get the spring stiffness of each oscillator because it didn't give you that. You'll solve for one value, apply to all. How do you do that here? Well, the way you do this, I mean, again, I'm not necessarily, I might ask you that, but is I already figured out that omega was 8 pi. I have T minus, yes, 7 minutes, sorry, yeah. Omega equals 8 pi. And if this is Hooke's law, and these are harmonic oscillators from masses on springs from question 1 and all the rest of the exam, then omega equals square root of k over m. So k equals omega squared m, and omega is 8 pi, and m was given as 20. So it's 8 pi squared, so 64 over pi squared times 20. Whatever that is, that's k. Like you can do, okay? So that's the answer to that one. Where to go? Then see at t equals 0 seconds, how high in meters is the 6th oscillator? Oh, that's a good question. Okay, so the way to do that is that forces you to understand the individual equations, which is what you should start with. So the individual equation for each one would be like, for the 6th one would be like y equals 0.03, because they're all the same amplitude. Y equals 0.03 cosine of 8 pi t, right? Because 8 pi, because they're all the same amplitude. So 8 pi t plus 6 times pi over 4. Like you just basically take their equation that they wrote up here, that I wrote up here, and just plug in 6. Or technically, I guess it's 0.06 in this problem, but you plug in, it's a 6 oscillator. So the point is that you plug in 0.06, its position, and that will take into account, so that will show you, so you can plug in and get the answer for the height of that one. Or there's other ways to do it too, but that's, if it asked you what's the height, you also could just read it off your diagram. If your diagram is good enough, I mean, precise enough, right? It's just asking how high is the 6th one. So last thing I'll say about that, I know I have 5 minutes. If it had asked how high is the, if it had asked how high is the 4th one, for example, like you could still do what I just said. You could plug in or you could read it off your diagram. But if you're understanding this concept, like if you're taking notes or you pro tip or you want to check later if you're really getting this, if it had asked, if question C had asked how high, if it had asked how high is the 4th one, well, you could do that in your head, like, or various easier ones like that. You could just picture it like because you know the very 0th one is at amplitude, right? And then because they're all separated by pi over 4, like the next one is halfway to equilibrium, but then the next one's at equilibrium. So then the 3rd one is halfway to the other amplitude position. The 4th one is at amplitude on the other side. Like I know in my head that the 4th oscillator must be at position negative 0.03 because it's got to be, because they're all separated by 1/4 of pi. So 4 oscillators later, it'd be separated by pi. That means on the other side of the cycle. If that's too much, I mean, maybe like write it down and think about it later, but anyway, either way, you could just plug in. Then D, it says how high is the 9th oscillator at a half period later, Again, what this forces you to do is either think it through conceptually the way I just did, right? Or it forces you to just figure out what a half period is and just plug that in for time into the equation for the 9th oscillator. Like you could do that. And how do you know what time to plug in? We said before, the period for this whole thing is 4 seconds. Now, again, of course, I'm speaking fast. And again, and I think most of you do know this, mostly what I'm giving you now is the stuff to write down to then think about and check with yourself as you're getting it better later. Like even I am not assuming that everything I'm saying right now necessarily makes sense. But I'm definitely convinced now that we're screen sharing this and talking about it, now that Chris just like cajoled me into giving away answers, I absolutely think this is good practice. Like however I write the question for your actual exam, like, and especially if you can get together and talk about it with one another, which you're allowed to do even after Thursday, just not with me. Okay, so that would be so D. So I'm not saying the answers, but I'm telling you how to do them. So D, you would solve for the period, which is definitely 4 seconds. Which is 4 seconds. So a half period is 2 seconds later. So you just plug in 2 and solve. All right, then the rest of it, interesting. Oh, no, okay, wait. So then pulse is propagating. We've 2 minutes. Where it says to the Doppler effect, we just started that, and I won't ask you about the Doppler effect on your exam. We're not up to that in your exam. But pulse is propagating is the wave piece. So in 2 minutes, I can do this fast. Emitters determine the wavelength for these waves. The wavelength for these waves is 2 pi over 4. I mean, it's 2 pi over 4, which means it's 4 pi, which really makes sense if you really think it through. That means I won't get into it. But that's what it is. How did I get that? I got it because K equals 2 pi over the wavelength. Definitely, by definition, if you understand K, just like omega is 2 pi over the period, and that's how I got the period before. So K is whatever I just said. Then what was the other? What's the frequency? We already said it's 1/4 of a hertz, right? Yeah. And then the speed. Okay, this is where we're in. Perfect. The speed is omega over K. That's the last thing that you're responsible for, and that we proved like the last thing, like last week. Speed of the wave is omega over K. in other words, it's lambda over t. It's how far across the wave is divided by how much time it takes to get across the wave. It's lambda over t. So if the wavelength, I think we said was 4 pi, and you could triple check me on that. If I made a mistake while I'm speaking, but the wavelength is definitely 2 pi over 4. 2 pi over 5. So you do the math. It's 2 pi over 4. Oh yeah, so it's just 8. Sorry. So the wavelength is just 8, not 8 pi. It's just 8, the wavelength. 2 pi over 4. So the wavelength is 8, and the period we said was 4 seconds. So it's 8 meters over 4 seconds, 2 meters per second. That's the speed of the wave. And that's it. Yeah, if you can do that, okay, well, it's 1:30. So I'm done. Good luck. I'll post it by 8 p.m. tomorrow night. I know you're all going to totally rock now. Your questions were good. Hopefully this, I like the way Chris, okay, great. Okay, so I'm here to answer any, if you want to hang out for a second, that's fine. In fact, you could totally, we can make this total office hours. If you want to really hang out, you can. But you have places to go, so go, but I'm not going anywhere until, okay. Bye. Yes, have a good day. I'll turn off the share.
Oh, Professor,
Yes. I'll turn off the recording too. Hold on one second.
this is a friendly reminder.